Good afternoon. Okay, so last class we have discussed some NP problem and uh, some of the reduction between those problems, right? So just quickly review those problems, right? So when we talk about P, right? P represents the category of the problem that we have polynomial time algorithm to solve it, and NP it's representing the set of problem where to verify the result, we can done in polynomial time, right? We can verify the solution fast, but to solve it, we don't know there is a official algorithm, right? So we don't know there are any polynomial time algorithm. In last class, we have C independent set problem, right? To find the maximal independent set, where given a graph, we're trying to select the maximum amount of vertices so that no edges are belongs to this subset. Where the vertex cover, again, we are giving a graph, and we're trying to select the vertices so that our selection of the vertices covers every single edge. In other words, every single edge must have at least one of the endpoints in our selection. And we're trying to select the smallest edge. So that's the minimum vertex cover. So normally for the cover question, we will look for the minimum amount. In last class, we have showed that the independent set and then the vertex cover, they are complement of each other. So if we have find the maximum independent set, then taking the complement, we can find the minimum vertex cover, right? Then we see how the reduction works. When we talk about problem 1 reduced to problem X, that means we are assuming we're trying to solve problem 1, and we have the algorithm for problem X, and we're trying to use the algorithm of problem Y to solve, we're trying to use the algorithm for problem X to solve Y. Now to show this, we need to first convert the input, right? Because we are giving problem Y. So if you convert our problem Y to problem X, we need to convert the input. So we can use this algorithm. Then and since we have this algorithm for X, we need to convert the input to X, then we can use this algorithm, and this algorithm will give us the result for problem X. But we're trying to solve for problem Y, so we need to again gonna convert the result back. Right? Now we don't need to show the algorithm, right? The algorithm part is what we assume that we have. Right? So to show the reduction, we want to show the first step and the last step to show that we are able to convert the input over to use the algorithm. And when we get the result, we are able to convert the result. That's what this is saying. So we are able to solve it using the algorithm with some additional polynomial. Right? So that polynomial work is the time that we take to do the conversion. And this reduction is written as the problem Y is polynomial time reducible to X. And that means Y is at least, that means X is at least as far as 1. Because you can use X to solve 1. So that means X is at least as far as Y in order to solve the problem. You see that? If you are capable to solve a problem, that means your machine must be at least as capable for that problem. And then you might be able to solve the harder one. Right? Yeah. So that's why when we reduce the problem Y to X, we say X is the harder in that sense. It doesn't mean the runtime, right? Because the runtime for Y could be the same or could be more than X. Okay. So last time we have seen that the maximum independent set and the initial cover, they are able to reduce to each other. And then we also have seen the decision version of the problem. So for the decision version of the problem, we are focusing the question with a yes, no answer. Now for all the general automaticity question with the min or max, we can easily convert it into a decision version by providing the additional value k. Right? Then the question becomes, can you find such and such with size at least k or at most k? Right? Depending on you are working with the minimum set or the maximal set. Okay, so last class we have shown that the general version can be reduced to the decision version. Just iterate through the K until you find the answer switch, then you know what's the minimum or what's the maximum. Or you can start from the highest, going down until the number switch, then you find the minimum, right? 1.9, right? And to reduce decision version to general version, it's very easier, right? You just compare the little k with the final result, or with the general result. Then you can immediately know to answer yes or no. Good. And we ended by the set cover question, where we're trying to reduce the vertex cover to be set cover. Right, last class we see that we cannot do vice versa. Right, because giving a set, we can always construct a graph with, but we can do the other way around. Okay, so just review the problem. We know that in the set cover problem, we are given a set of an element, right? That's the universal set, and we are giving a bunch of subset. The union of those subsets will be the universal set, and then we are giving an additional value. Okay, that's looking for the decision version. Can we find a collection with at most k of those subsets to cover all the elements? This is an example from last class, if you don't remember what this is. Right, so here we have 10 elements, and then we have a bunch of them, right? So the question is, how can you select those subsets to cover all the elements? And we want to, for the cover question, we're trying to find the minimal amount of subset that we need to cover all the elements. Okay. Now the question here that we're trying to answer is vertex cover reducible to the set cover? Right, in order to do that, you look at here the step. We are assuming we are giving the input for the vertex cover. We're giving the graph. And if we know how to solve the set cover, how do we use set cover algorithm to solve the vertex cover? Right? So that's for the reduction. If we try to reduce vertex cover to set cover, that means we try to solve vertex cover, then we have the algorithm for set cover. That's normally how we do reduction. When we also use a problem that we're trying to solve to a problem that we already know an algorithm. Yes.
Wait, so we use the algorithm. So we assume we found an algorithm for set cover.
Yes.
And then we use that, and then we're showing that if we have an algorithm for set cover,
You can solve vertex cover.
by doing a little bit extra work.
Yes, the conversion. That's what reduction is. Right, so whenever you trying to show that your problem can be reduced to existing problem, then you try to show that given your problem, you are able to reduce to an existing problem with their algorithm. Assume there's any. They can just use their algorithm, get their result, convert the result back to solve your problem. That's what we have. So put that here. The work that we need to show, the first step is to convert the input from our problem to their problem. And then we can just use the algorithm. We don't need to do step 2, but this part is assumed. Regardless, we actually have the algorithm. If they have it, great, you just use it and then get the result. If we don't know how to solve it, then wait until someday someone figure out the algorithm, then you know your problem can also be solved as soon as someone solves that problem. You see that? Okay, so step 2 is assume. Now, once we get the result, we want to see how is their result are able to convert it to your result. So what you need to show for the reduction is step 1 except convert the input and then convert the output back. Okay. Now, last class we kind of talked about how to convert it over, right? So in the vertex cover, we're trying to use vertex, or we're trying to use vertices to cover edges. In the set cover, what are we trying to do? To select the subset to cover all the elements. So what does the vertices correspond to? What does the vertices here correspond to? Elements. Let me repeat that again. In the vertex cover, your vertices, you're trying to select vertices to cover edges. In the set cover, you're trying to use your subset to cover the elements. So what does the vertices correspond to? The subset. What does the edges correspond to?
The element.
The elements. Do we see that? So when we do the conversion,
That means the vertices that correspond to the subset, the
elements
elements that correspond to the
edges.
edges.
Now I think someone is talking here. Let me mute them. Okay. That student left. I think I heard something, so you probably hear it in the recording if you watch it, but I don't know what that is. Okay. Okay, so let's look at the work here. Right, so this is the word diagram for the previous. Okay, so we are giving a vertex cover. Right, the vertex cover input is a graph. Right, so you are giving a set of vertices and edges, which is going to be graph. Now for the decision version, we are also giving a value k. Right, for the decision version vertex cover. Like, can we find a vertex cover with size m? Most. Okay, now to convert it into set cover, we need a universal set and then the subset. Then we just said earlier that the universal set is representing the edges. Right, because the elements are corresponds to the edges. So we will have all the edges in the original graph. That's our universal set. Then we will have the subset here representing the vertices. Right here, each vertex in the graph, we will make a set, or we'll make a subset, where this subset will equal to all the edges incidentally, which means you have all the edges that connect to that vertex as one equal. Okay, then the k will be the same. Right, so that means on problem I, you're looking for, does there exist a vertex cover with size at most k? Here, you're trying to look for, can you find a set cover with size at most k? Same exact. And how do you do this? You look at here. This is the same graph that I get when we talk about independence and vertex. Alright, so that's the graph. Now to convert the input, here, the universal set is all the edges. I label the edges, so I have 8 edges here. That's our universal set. Now each of the vertex that you look at, vertex 1 is translated to subset 1 because they only have 1 edge connected. You look at 2 has 3 edges connected to it, 2 E1, E2, E3. You look at S2, we have E1, E2, E3. So that's a total of 7 subsets. You see that there is a one-on-one relation. Now, can you find me a set cover here? Any set cover. Can you find me any set cover? What is it? S2? S4? And S7. Okay, so if you look at here, if I take union of this 3 set, what do we get? Okay, E1, E2, E3, E4, E5, E6, E7, E8. Isn't that all the elements in the universal set?
Yes.
Yes. How do we convert the result back? Which vertex will you select for the vertex cover? 2, 4, 7. 2, 4, 7. You see that? So once you find a set cover, you just need to look for the corresponding vertices. So here you have 2, 4, and 7. And that will cover all the edges. Right, so the selection here is the same. So I can make the following claim. U can be covered by K of the sets in SV, where V is belongs to some of the corresponding vertices. If and only if, so that means this is a strong guarantee, there is a vertex cover of size K in G. So this is an if and only if statement, so it will either prove it by contradiction or show that one implies the other, and then you reverse. So in other words, if you want to show that if there is a set cover with size K, you can always find a vertex cover with size K. And vice versa. If you can find a vertex cover with size K, then there also exists a set cover with size K. You say that out of if there's a one-to-one relation out of the selection. And explain why it always exists. Okay, so I won't write down the proof. So I will leave the proof for you to do as the exercise. Okay, and then if this claim is true, or let's assume this claim is true, then giving the input I, that's the input for the vertex cover, we can convert it to I prime, or we can convert it to the set cover problem. And then we're gonna fit this input I prime to the set cover algorithm. A. Then if this algorithm returns yes, then we will also return yes to our problem I. It's the same result, right? Because if there exists a set cover, I can translate it to our vertex cover result. So if the answer is yes to their if the answer is yes to their result, then the question to our problem for the vertex cover will also be yes. If they return no, then we will also return no. So otherwise, return no. Good. So for the decision version, the result is the same. If we are looking for the general result, then whenever you can find the minimal set cover, you can just do a direct translation to get the result for the vertex cover. Are we good? Question? You see how this works? We are able to convert the result back. Assuming we are able to solve the set cover, then we can solve vertex cover. Okay. Now let me give you another problem. I'm gonna give you a few more problems in the NP. Now the next problem that I showed you is actually one of the famous problem in the NP category. And this is actually the first problem that proving to be NP hard. What does it mean by NP hard? NP hard means is the hardest problem in the NP category. By hardest problem, that means any problem in NP is reducible to this problem. That's proving. That direction is proving. So in other words, if you can solve this problem in polynomial time, you can solve every problem in the NP. That's why it's called the NP hard. NP hard means it's the hardest problem in the NP.
It's like the one you get like $.
Yes. Yes, yes. so if you can solve this in polynomial time, you pretty much answer the P equals to NP question. If you're able to solve this in polynomial. Now, there are variants of this question, like where if you don't do the deterministic algorithm, there is like a randomized one. I think you will understand, where you are able to solve it in polynomial. But that's a randomized, like with a high probability you can get a result, but that's not enough. Okay, so there are a lot of study people done it. Okay, so, but we're not gonna do the proof in this direction, it's because it's hard, it's like a hard one. Okay, but this is an NP problem. And now, since we know, taking the fact that this is the NP hard, that this is the hardest problem in the NP category, if you can reduce this problem to any of the problems that we already know, or that we already seen so far, then that will show that our problem is also in the NP. Yes.
So we can show that the independent sum problem is NP hard with this problem.
Yes, we could. If you reduce this problem to independence, which we will actually show. Okay, so like, so far I only, like, so we see like a problem in NP based. We can verify the result in polynomial time, and we can verify the result fast, but to solve it, we don't know a fast algorithm. This problem, people prove to be in NP hard. It's as hard as any other problem. Now, if I can reduce this problem to our problem, that means our problem are able to solve this. But we just say that this is the hardest one. So if this can reduce to our problem, like the problem that we already know, that means our problem is as hard as this one. So our problem will also be in the NP hard category. So any problem in that category, if you solve one, you solve all. Just by doing all the recounting. Okay, now let me introduce the problem. So it's called reset. You've probably seen this title before. Now the set here is representing, it stands for the satisfiability. What do I mean by that? So in this problem, you are giving n variable. And those variables are Boolean variables, means they are either true or false. Now in the base notation, the value will be either 0 or 1. 0 for false, 1 for true. And in the degree set, you are giving a formula, which means you are giving a Boolean expression, where this formula is made by n clause. So you have, it's by conjunction of n clause. Conjunction means the n relation. So you have C1 and C2 and C3 up to Cn. Now what's a clause? A clause is a disjunction over 3 variables. Disjunction means the OR relation. So you can have variable 1 or variable 2 or variable 3 with the OR relation for each clause. Yes.
Why is there an extra?
The bar
Yeah.
there means you can negate the bar, right? It's a Boolean variable. So if you see the bar there, that means you are taking the opposite, the negation of the variable. So when we talk about 3 variables, the variable can be negated. Okay, so that means you are working either with the variable or not the variable. Okay, now it's called 3 set because each clause has size 3 or up to 3. So you can imagine there are 2 sets, there are 1 set, and there are k set problem. Why is 3 set special? Because if you look at this problem, right, 3 set is actually the first k set that's in. Okay. So if you look at this, right, the formula is made by conjunction of n clause. Conjunction, you have a bunch n. When you have conjunction of a bunch variable, how can this expression to be true? You have clause 1 and clause 2 and clause 3 and clause 4. How can you make this true? They all have to be true. If any of the clause here is false, then that will make the whole formula false.
And it'll be messed up.
Yeah, so if I want this to be true, then all of them need to be true. Do you see that? And each clause is made by disjunction of 3 variables. So what does it tell us?
It's one.
At least one of the 3 need to be true, right? One or the negation of it. right? So at least one. It doesn't need to be all, at least one. It could be two, it could be three. I only care about you have at least one. But if all of them are false, then that clause is false, then that will be the whole function. With that said, imagine you have one set. What does one set mean? There are only one variable in each class. How long does it take you to verify this formula is satisfiable? Satisfiable means this formula can equal to true.
Constant.
How is it constant? How do you figure out what to assign to each variable? It should be linear. What do? If this is one set, I mean each class here is a variable. And you want all the variables for each class to be true. So that means we'll go to the first class and you set that variable to 1, because the variable could be negated. So you need to set this to 1, set this to 1, so we'll go through the class, set each of them to 1. Now, if any of them are contradicting each other, then this formula is not satisfied. By contradicting means it's possible that a variable appears twice, and one of them is the negation of the other. Right, so you might see x1 somewhere, and then not x1 somewhere. And you cannot set both of them to be true. We see that? So that will take, what's the runtime for that? O n, because you have n class.
So we're checking each.
You check each class. Each class, for one set, each class has one variable. So to determine whether this formula is satisfiable, if so, if you want to come up with the assignment for those variables, that will take O n. Okay, for one set. Okay. Now for two set means there are only two variables. Between the two, one of them needs to be true and then you can check. So for that, for two set problem, there are also a final method of. Or that problem can be solved about. Actually, since you are doing the randomized algorithm, like or the approximation for the three set, another presentation or good presentation, someone can look at the algorithm for two set. To show that what's the algorithm for that. That one has a official, but not this one. Okay. So now here's an example, right, for the three set. We have three classes. Okay, now the question to the three sets, given this formula, can you set the variable, right? Can you set each of the variable to either 0 or 1 such that this formula is satisfied? Satisfied means you set it to true. Okay, so if you look at this example that I give you, if I set all the value to 0, is this formula true or false? If you look at the first class, is first class 1 or 0? 1, because the x2 there, when you negate x2, it's 1. And let's look at the class 2.
Oh.
It's true, right? When you negate 0, you get 1. The last one, it's also 1 because you are negating 3 or 1, and then negating the 0 give you 1. So you have 1 and 1 and 1 that give you 1. Again, those conjunction means and. In the class, you have the or relation. Okay? Let's look at another one. What if you assign each of the variable to 1? What's the first class? True. 1, because x1 is true. What about the second class? 0. Because you're negating all the 1 and you have 0 or 0 or 0, that gives you 0. And then you don't really need to check the third class.
0.
But the last one is 1. But this whole thing gonna evaluate to 0. But we are able to find an assignment that make the formula true. So this formula is satisfiable. Okay? Now, given this formula, how do we know this formula is satisfiable? Can you come up with an algorithm? A naive algorithm. Brute force.
Oh, just check if check the clauses. If the conjunction of clauses is here.
How do you do that? You're gonna check what? All the assignment. You want to check all possible assignment. How many possible assignments are there? You have 2 to the n. Why 2 to the n?
As, and as many, inputs.
No, we have n variable.
Yeah.
We have n variable. Each variable can be
0.
0 or 1 for each of the n. So I have 2 times 2 times 2, n of them, so 2 to the n. Okay? Now what's the runtime for the brute force? How long does it take to verify one assignment? N. No, m. You want to verify each class. Each class has only 3 variables that take constant, but you have m of them. So the runtime will be O 2 to the n times m. That's exponential time, right? Not polynomial. So that's why this is not efficient. And the fact that I told you this is in the NP hard, we don't know any polynomial time algorithm for it. Okay. Now let's try to show that one of the problems that we already seen earlier are also in this category. And let's pick the first one, the maximum independent set. Okay. So now we want to show that 3 set is polynomial time reducible to MIS, right? The maximum independent set. How does this work? Or how do we show this?
Set.
So we are giving an instance, right, or input of what? Of 3 set. And input of 3 set is a formula. And we are also giving, or assume we are giving an algorithm A for what?
For the
Same as for the input, let's call it I. Right now, the goal here is to solve our input using this algorithm with maybe with some extra polynomial work. Right, the conversion, as long as you show that your conversion take polynomial time. Okay. So the first step is to convert the input, right? So giving input I of 3 set, we're trying to convert the input from 3 set to MIS. So from there, we will have input I prime of maximum independent set. Right, so this is the step 1. All right, now step 2. Now, once we have the input here, then we will feed it to the algorithm of MIS, get the output of MIS. What's the output of MIS? What's the output of MIS? What is it? The vertices of the graph, or the maximum amount of vertices that we can select without edges, right? Then we're trying to convert the output of MIS to output of our 3 set. Right, so output of MIS is select. It's a selection of vertices without edges, or the maximum of them, right? So that's the max selection of vertices without edges, where the output of 3 set is what? What's output of 3 set? True or false? Is it satisfiable? So in other words, we want to output an assignment of x i's if f equals to 1, or f is unsatisfiable. Unsatisfiable means there's no assignment to make it true. Okay, so if you look at here, this is step 3. We need to show step 1 and step 3. Now to get the output here, this is step 2. We don't need to do this, right? This part is assumed. We assume we have this algorithm, or eventually someday someone gonna give us this algorithm. Okay, now let's look at step 1. How does step 1 work? So for this step 1, let's go back to step 1. What's the input for 3 set? A formula. What's the input for MIS? A graph. So that means the question now is, how can we build a graph from 3 set formula? Right, so that's the question that we're trying to solve. Now let me give you the rule. Okay, so that pretty much answers the step 1. Okay, now let me take down the formula. Let me take this formula, or let's convert this formula. Okay, now I won't write out the rule. I will just tell you. You can write it down. Okay, so for each class that you see in the formula, you're gonna draw a triangle. Basically gonna draw a triangle. This is 1. I have 3 class, so I need to have 3. So I have 1, 2, and 3. Okay, so I have 3 triangle here. Okay, now I have each triangle has 3 vertices, right? Now I have each vertices, or I'm gonna have each vertex represent a variable in the class. So if you look at the first class, we have x1, x2's complement, x3. For the second class, I have x1's complement, x3's complement, x2's complement. Okay, now for the last class, I have x2, x3's complement, x1's complement. Do you see that? So that's the first step. For each class that you see in the formula, you're gonna draw a triangle, and then label each vertex by the variable. Then step 2, you're gonna connect each vertex with its negation, or its negated variable. So if you look at the first one, you see x1. Are there any x1's complement?
Yeah.
Yes, then you're gonna connect them. So for any one that you see, you connect it. So every verse is gonna connect that to all its negation. So if you look at x2's complement, are there any x2? Yes, there's one on the top. Okay. Are there any more x2?
Yes, no.
There's x2's complement. Anything else? x3. x3 with x3's complement. x3 with x3 complement. Anything else? Are there any other complement that we are not, or negation that we are not connecting? No. Okay, so that's it. This will be the graph that we're working with for the maximum independent set. Do we see how we do the conversion? For each class, we're going to draw a triangle, label each vertex by the variable in the class. Then connect each variable to its negation if there are any in the graph. You're going to connect all of them. Okay, so in other words, every vertex represented by one of the variable is connected to all the other negated vertices. Okay, then you will run the MIS algorithm. Look for the maximum independent set. Okay, so let's find the maximum independent set here. And we're gonna highlight the selection. Okay, now let's look at the first triangle. Okay, out of the first triangle, we have 3 vertices there. How many vertices can we select for the maximum independent set? Out of this triangle, how many can we select? At most 1. Do we see that? For each triangle, we only select 1. What happens if you select more than 1? Can you select 2 from the same triangle? No, why not?
Because it has the same.
It has an edge. No matter which 2 you select, there's an edge between them within the triangle. So with that saying, for such a graph, how many vertices can you select maximally? What's the maximum amount of vertices you can select in this graph? 3 in this one. In general, how many? M. Right, because we have 1 triangle for a class. Right, this graph is converted from the formula. So if the formula has M class, you're gonna have M triangle. So the size of, so let me write it on the side. So now we see that the size of MIS will not exceed M, where M here is the size, is the number of triangles we have. The triangle here means the class, number of class we have. Do we see that at most 1? Now the reason I say it's at most 1, right, less, it could be less than M, because it's possible that a triangle is connected to all the negated variable. And if you select all the negated variable in the previous triangle, then it's possible to have a triangle that you cannot select any. Do you see that? Okay, now let's look at here. For the first triangle, pick 1. X1, sure. So let me highlight X1. Now after you select X1, what can you not select?
X2 and X3.
Everything in the same triangle. What else can you not select? All the X1's complement. Right, because all the X1's complement are connected to X1. Now let's look at the second triangle. What can you select? What can you select in the second triangle?
X3.
Either not X2 or not X3. You cannot select X1. But because there's X. You can select 1 or 2. So which one do you want me to select? Okay, not X2. So let me change your color. So you want to select not X2. Now after you select this one, which one can you not select?
X3.
Everything in the same triangle, and it's the negation of it, so X2. Okay, so now we go to the third triangle. Which one can you select?
X3.
X3. Do you have choice? No, right, because for the other 2, you selected the negated. Okay, so we're done. Yes,
And so I'm guessing that in second triangle, if you select not X2, then not X3 actually. you
Okay.
Have to select X2 in the third one.
no, if you select that X3 here,
Yeah.
you can still select that X3 here,
Really?
because the not X3 are not connected. So you can select the same label, but in a different version. So you are able to select the same label, but the version representing the same variable, that's fine. But you cannot select a variable with its negation. Okay? What's the size of this maximum independent set? What's the size of this maximum independent set? 3, right? Which is number of the class we have here. So that's the maximum amount of maximum independent set. Okay, so we'll just say that the size of maximum independent set cannot exceed n, and then we just find one that matches n. Just the maximum amount that we can possible. Now, we have the result for the maximum independent set. How can we convert the result back? How can I use this? The selection of the vertices to answer, is this formula satisfiable? Take a guess. What do we do with those variables that we selected? What? No, we're done with the graph. We have the output. If you look at the chart that we see earlier, we're done with the step 1. We're done with the step 2. Right? Now we already have the output for MIS. Right? We select the vertices without engine. We're done with this. That's the vertices that we highlighted. Now the question is, how do you convert the result?
Grab the vertices that had a and statement.
Okay. The output we have here is the selection of the vertices. What are we trying to get? The assignment of the variable to make the formula true. What's the assignment? How is the selection here corresponds to the assignment? Okay, so let's look at each triangle. It corresponds to a class. You see that? And each vertices is representing a variable in this class. Yes? Okay. Now, how do we make this formula true? Earlier we discussed that. If all true, if all the class are true. Now, how do you make a class true? If one of the variable is true, which variable do you make it true? The one that you select. Do you see that relation? So if you are able to select one vertex from each triangle, that means if you make the selected one to be true, that means from the first class, there's at least one that's true. From the class 2, you are able to pick one that's true. From the class 2, you are able to pick one that's true. It's okay to have the repeated one, because the same variable can make multiple class true. Are we good? Now let me write out the last step. Okay, so from step. Now for this particular example, we have what? X1 equals to 1, right? That's a selected vertex. And then we have X2's complement equals to 1. And then we have X3's complement equals to 1. To convert it, X1 is equal to 1. What does X2 equals to? 0. X3 equals to?
0.
0. So if you verify it, 1, 0, 0 will make this true. But if you look at the first class, you have at least 1, 1. The second class, you have at least 1, 1. For the third class, you have at least 1. Yes. You can have multiple assignments. That also means you can have multiple maximum independent sets. Right. So as long as you can come up with a maximum independent set with size equals to n, then your formula is satisfiable. So let me write out the result. So for step 2, right? So to solve it is the step 2. So for step 3, right, step 3 is to convert the result. So to convert the result, there are 2 cases. Case 1, the size of maximum independent set is equal to M. Or the size of maximum independent set is less than M. If size of the independent set is equal to M, that means you must select one vertex from each triangle. We have M triangle. You need to select one from each triangle. Then F is satisfiable. Now, if it's less than M, that means there must exist some triangle where you're unable to select any. Now, if there exists a triangle that you cannot select any vertex, that means that corresponding class is not satisfiable. So that means all the variable is 0. You are not able to assign 1 to. Then, if any one of the class is 0, then the whole formula is false. Then the formula is unsatisfiable. Okay, now for the formula that's satisfiable, then the assignment is corresponds to the selected vertices with value set to 1. But you only do this if it's satisfiable. If it's not satisfiable, right, if the size of maximum independence is less than M, then your answer is unsatisfiable. You don't need to come up with the assignment. There's none. Are we good? So let me give you another, or let me just give you a quick exercise. So if you have a formula with x1 or x2's complement or x3, and you don't need to hang this thing. You don't need to turn this in. We will work it together. You have x1's complement or x3's complement or x4 and x2 or x3's complement or x4's complement, x1's complement or x2 or x4. Solve it. First, how do we convert this to graph?
Make a triangle.
Make triangle for each class. So we have this is 1. This is 2. And then we have 3 and 4. Right now for each triangle, we're gonna label its vertices by those variables. Then what? Connect the negation. So x1, x1, x2, that's the x2, There's another x2. Here is x4. Here's another one with x4. This is x3. This is another x3. Anything else? Did I miss anything? Did I miss any edge? Should I zoom in? Did I miss any edge?
I see.
I think that's all. Okay. Now let's try to find the maximum independent set. From the first triangle, which one can you select? Any? So which one do you pick?
X1.
X1, sure. From the second triangle? Not x3 or x4. Which one do you want to pick? Just pick one. It doesn't matter. Just
Four.
okay, sure. X4. Which one can you select for the next triangle?
Not X3 or X2. X.
Can you choose not x3? Yes. Or x2. Which one do you want to select?
Two.
X2, sure. Last triangle.
X4.
Sure, you can select S4 again. Okay, so you can select S2 or X4, anything but not X1's complement, or not X1. Okay. That means it's our formula satisfiable. Yes. Why? Because we are able to select one from each triangle. Now, what's our assignment? X1 equals to 1, X4 equals to
One.
1, X2 equals to
One.
1, X4 equals to 1. Now, it's okay to select the same variable multiple times, right? Because you just set it to the same value, right? So that's why, so that should explain why we connect each variable with its complement, right? Because we don't want to select a variable with its negation at the same time, because we cannot assign both to one. Yes,
Wait, so in that case, because X3 is not selected, it doesn't matter what X3
that
is.
means you can assign any value to it,
And
0 or 1.
because then all the classes still true.
Yes, yes. So if you see a variable that's missing, that means you can set it to anything you want, right? That means the class are already will already evaluate to true by the current variable. So if you look at here, you can have x1 evaluate to 1, x2 evaluate to 1, x3 anything, right? 0 or 1 doesn't really matter, and x4 equals to 1. Now, again, this is not the only selection, right? It all depends on how you pick the maximum independent set. Are we good here? Okay, now let me introduce you another problem. Okay, and that's the Hamiltonian cycle. Now, you probably heard this term before, right? In 220, have you heard the Hamilton path or Hamilton circuit? What's Hamilton circuit?
It was like in relation to like, was it a city? Like, I think it was.
No, I think you are thinking of the different portion.
Like,
Yes. So for the Hamilton cycle, or that's equivalent, the Hamiltonian cycle is equivalent to the Hamilton cycle. It means you're trying to find a circuit or a path where you start at one of the nodes. So you're giving a graph. You want to start at one of the vertices and go through every vertex exactly once, and then go back to where you start with. You don't need to go through every edge, just all the vertices. Yes.
Isn't that the traveling salesman problem?
Travel salesman question has an additional constraint where you're trying to find the smallest Hamilton cycle.
So if I can solve that one, I can solve this travel.
Which one's harder? Is this one harder or Hamilton? Or the travel and salesman problem?
What was the other part?
The travel and salesman problem is you're trying to find the smallest Hamilton cycle. Because in the trouble itself, question, your graph is a weighted graph, where each edge has a weight on it. Think of the weight as a distance. So you try to find the Hamiltonian cycle, and you try to find a route that causes
So then it would be traveled
traveling salesman question
because of the weighted part.
because of weight. But because with this, there's no weight.
Oh, and here, and I
So you
can
can actually,
reduce it
you can
to
reduce this problem to traveling
by
salesman.
adding.
Yeah, so if you can solve traveling salesman problem, you can solve. That's actually the next question.
Oh, wait, so this is not NPR then?
This is NPR. Well, if you can reduce 3 sat to this, then it's NPR. The answer is yes, which we're gonna show. Okay, now are we clear with the definition? Giving a graph. If there exists a cycle in the graph where it goes through every single vertex exactly once, that's the Hamiltonian cycle. And the question is simply, does this graph contain a Hamiltonian cycle? That's the yes one. Or you can ask for specific. Right? Normally, if you are able to answer yes and no, you are able to find one. Okay. So the question should be straightforward, but to solve it is hard. Now, if I give you a graph, does this graph have Hamiltonian cycle? Go through every single vertex exactly once.
Yeah.
Exactly once.
Well, you still gotta go back to the start for it.
Yes,
Then no.
then no. Right, so for the cycle, you start at a vertex, go through every single vertex, and then go back to where you start with. This is not. But if I add the edge on the bottom, then that will be true. But this one is not. No. If I add the edge on the bottom, then yes. Okay. Now to show this question is NP hard. You're gonna show. Because the only problem that we know it's NP hard now is what, 3 set? And we have showed that maximal independent set is also NP hard, right? Because we just reduced 3 set to maximal independent set. Now, if we can, that means any problem that we reduce the MIS2, now they are all NP hard. Okay. So here we want to show that 3 set is polynomial time reducible to Hamiltonian cycle. Now, how do we do this? We want to do that, we need to show input for 3 set, which means a formula. So we want to convert input for 3 set, right, which is a formula. We want to convert, right, that's the step 1. We want to convert the input to input for Hamiltonian cycle, which is a graph or directed graph. Right. So directed graph means you want to find a cycle that follow in the direction. Okay. Then once you have the input, then you can pass into the algorithm for Hamilton circuit, which we assume we have. Then we will get output for Hamilton circuit, which means we know whether we have that circuit or not. And then I want to know, that's a step 3, right? Where we want to again do the conversion, convert the result back to output for 3 set. Output for 3 set is what? Assignment where f equals to 1 or f is unsatisfiable. Okay, now let me show you the step 1. Well, to do that, let's look at the input. What's the input for 3 set? What's consist in a formula? We have m clauses and n variables. We have x1, x2, x3, up to xn, where those variables are in either 0 or 1. And then we have the formula that made by class 1 and class 2 up to class m. And then each class is equal to xi or xj or xk, and then some of them might be negated. Okay? Now let's see how does the conversion work. And I will give you the conversion because the conversion is not so trivial. Okay? So we will start with a list of nodes. Okay? Now those nodes, and I'm trying to make a directed graph. Okay? Now between any 2 consecutive nodes in this row, you have edges going back and forth. Actually, let me. Okay? And I'm gonna have this row representing x1. Now guess what I do? How many variables do we have? How many variables do we have? N. So I'm gonna make m row. Okay? Then what I'm gonna do is I'm gonna create a starting node S. And I'm gonna have this starting node S pointed to the first node of the first row and then the last nodes of the first row. Okay? Then in between each row, each row will represent x1, x2, x3 up to xn. Then in between each row, I will have the beginning of each row pointed to the beginning of the next row and the ending of the next row. Same thing for the last node. I will also point that to the last nodes of the next row and the beginning of the next row. Okay? Then you will do that in between each row. Good. So again, this row will point it to the next row. Then I'm gonna have a sync node or the terminal nodes at the end where the last row, like 2 of its endpoints of the last row will point to it. Now remember we want a cycle. For the cycle, the last node need to point at the starting nodes. So I'm gonna have this last node pointed to the beginning of the nodes. Okay, now how many nodes are in each row? Well, in each row, there are roughly 3m row. There are roughly 3m nodes. Why 3m? I'm gonna explain. Like two. Let's see. If you reduce it to 2m, that's probably enough. But just to be safe, I will make 3m nodes. Okay. Now, for this current graph, do you see that you are able to find a Hamiltonian cycle? How do you find the Hamiltonian cycle? Starting from the source node, or starting from the first node, you can either go to the first row by going to the first node from the left, or going to the last node, right, or going to the right. Right. So when you can choose the direction, either you go to the left or you go to the right, then iterate through the entire row, then go to the next row. Now when it goes to the next row, you can pick to go from the left or go from the right. Right? If you go from the right, then you will go to the left and then go there. Now if you pick from the right, then you will iterate through the row, then you will end at the left, and then you will go to the next row. You see that? So from the source node, you can just go through each row in either left to right or right to left, and eventually reaching the last row. And then regardless you enter at the left or you enter at the right, you can reach the T and then go back to the source. Do you see that? So this current graph, I know this is crazy looking graph, but there exists a Hamiltonian cycle. The tribute. Yes. From the source node, go down row by row, pick up every single node, and then end back up. Now, what does each row here represent? The vertices, right? Well, sorry, not the vertices. Each row here representing a variables in the formula. Now, what does the formula make out of? Besides the variable, what else we need to have? The class. We only have a minute. So let's see if I can draw that in the last minute. Now let me give you a class. So suppose you have a class 1 that equals to x1 or x2 bar or x3. Okay, so suppose this is your class. Now what I'm gonna do for each class is I'm gonna create a new node for the class. Then do you see that this class has x1? x1 is the positive. So I have this C pointed out here. Actually, no, I will go from the row 1 from left to right. I will go from the nodes to the class and then going back to the next nodes. Then if you look at this C, it's going now for x2 is the x2 bar, right? It's not x2. So for not x2, I will do it backwards. So I will go from, so here I'm going from left to right. Now here we will go from right to left. And then for x3, it's the positive, so I will go from left to right. So the idea here is whenever I go to a row, left to right is representing 1. Whenever I go from right to left, it's representing 0. So now if you look at this graph, remember earlier I said we have a Hamiltonian cycle. Starting from S, you can pick up each row. Either from left to right or right to left, but you cannot change the direction in the middle. From which you can only go to each row that exactly once. Now remember here, going from left to right means 1. Going from right to left means 0. Now let's try to find the Hamiltonian cycle again. Starting from S. Let's say you want to go from left to right. Left to right means it's equal to 1. So from S, you start at the beginning, go to 1. Do we see that we can go to C1? And then go back to the very next node, so we don't miss that node. And then go to D. Then you just iterate through the rest. That's your Hamiltonian cycle. And we go to left to right. This is when the variable equals to 1. So you're gonna satisfy. You don't need the other. Right, so if you go from left to right, if x1 is 1, then this class, since you are able to pick up this class, is satisfied. That class is satisfied. Now, if you go from right to left, let's say you start from S, you go from right to left, will you be able to pick up C? How? If you go from right to left, at here, can you go to C1?
Oh,
No, the direction is different. Now when you go here, can you go to C1? Yes, when you go to C1, how do you go back?
oh.
Then you will go back to the previous node, then you revisit the node, so that means you are not. Then that's not a Hamiltonian cycle. So then if you go from right to left, that means x1 is 0. So if it's 0, then this is 0. Then you need the other variable to be true. So if you go from right to left, that means for x2, you should go from right to left again. Now from the right to left here, you can go from this node to C1 and come back. Because, do that here, it's in the reverse. You see how I set up?
Mhm.
For the x1, for all the positive variable, I have the connection from the left node going to the class, and then goes to the node right next to it on the right. Now, if it's negation, I will have the order flip. So I have a node from the right, go to the class, and then back to the node prior to it, right? The one right before it on the left. This way, you can convert the formula to a directed graph, where if you are able to come up with Hamiltonian cycle that pick up all the nodes with all the class, then your formula is satisfied. Think about it, and we will discuss this next class in your question. Okay, and think about your question, how to reduce this problem to child and salesman question, and that will be the last reduction. Okay. And we should finish all the material by next Monday. And I will give you a list of problems to expect on the final also next Monday. And for people who doing the presentation, you can start doing, if you're not really next Monday, if we finish the class early, you can do it Wednesday or the following Monday.
Also, we have 3 classes left.
We have next week and then that following Monday. And then your exam is that Wednesday. So exam is 2 weeks from today.
Okay. We need to do to present it.